Hello, my name is Chabo Edna Takaisa from Group SWML24 with the project True Time Biomechanical Skill Classification for Motorcycle Dispatch via Edge Optimized Convolutional Neural Networks. This presentation is going to cover the model selection and deployment section of our project. Well, our project initially has two datasets, the first one being the UCF101 dataset containing the biking video clips, and the other being the RoboFlow dataset containing the still images of cyclists in the varied environments. This is the dataset I'm going to be using today to train my four models. My first model is the K-means clustering algorithm, which is an unsupervised algorithm that groups cyclists, in this particular case, into distinct non-overlapping clusters by minimizing the distance between each data point and its cluster centroid. Specifically, it operates on a 7-dimensional biomechanical feature vector representing one vector per cyclist and partitions them into K clusters by minimizing the within cluster sum of squares. K-means works in such a way that it treats each cyclist's 7-feature score as a single point in a 7-dimensional space, and the algorithm alternates between two steps, the first one being the assignment step, whereby every point is assigned to the closest centroid using the Euclidean distance, and the second step being the update step, whereby each centroid moves to the mean position of all points assigned to it. This repeats and goes on and on until the centroid no longer shifts, hence the clusters have converged. Moving on to our architecture for K-means, our input is X-scaled, which is our scaled feature matrix, and the algorithm initializes centroids, runs the assign and update loop until convergence. The outputs had cluster labels from 0 to K-1. These labels then map directly to our 3 rider tiers, which is high skill, moderate, and developing. Under K-means, we have parameters, stroke hyperparameters that we use. And the first one I'm going to talk about is the number of clusters, which has been equated to 3, aligning to our 3 intended skill tiers I've talked about in the previous slide. Then we go on to talk about the initialization parameter, which is equated to K-means plus, but this is default in the escalons. We move on to maximum iterations, and here we have equated them to 300, which gives our algorithm sufficient steps to converge. Our tolerance is 1 exponent -4, which stops execution once centroid movement becomes negligible. And then for our number of runs, which has been n init is equals to 10, means that our algorithm runs 10 times from different random seeds and keeps the best outcome. Next, we look at our explainable AI techniques, and in this case we have 5. The first one being the silhouette plot, which shows how confident each rider fits their each rider is able to fit and compute their assigned tire. Then we have the between cluster variance, which identifies which of the 7 features most separate the tires, whereby our red bars are our 3 new features. For the radar stroke spider chart, this one maps each cluster's average feature profile so that you can confirm high skill riders genuinely by scoring higher on balance and posture. Then we have the PCA to D scatter, which compresses the 7D into the 2D using the PCA transform to visually confirm clusters are well separated. Lastly, we have the confusion matrix, which tests tire labels against a KNN reference to check for mislabeling. The following slides are the ones showing these images of the explainable AI techniques. Well, this slide shows the k-means PCA scatter as well as the between cluster variance chart that I have already explained in the previous slide. And then for this other slide, we talk about the radar chart as well as the silhouette plot, which have also been discussed in the previous slide. For the text accuracy, our k-means achieves a 98% overall accuracy on the 934 test samples that we have evaluated. Next, I'm going to move on to the next model. Yes. Our next model is the DB scan, which is the density-based spatial clustering of applications with noise. This one basically groups points that are closely packed together, which are the high density, and marks points that are low density regions as noise. For the architecture, still our input, we have the X scaled, which is the scaled feature matrix, and our key parameters, we have the neighborhood radius, EPS, as well as the mean samples, which are the minimum number of neighbors required from the dense region. For processing, we find neighbors of each point within the neighborhood radius. We identify core points that are greater than or equal to the minimum number of neighbors required to form the dense region. We form clusters by connecting the core points that are within the neighborhood radius. We add border points to the clusters and label the remaining as noise. So our output is the cluster labels, and the negative one is for the noise. DB-scan works in such a way that it classifies every point as one of these three types, whether it is a core point that has at least mean sample neighbors within the neighborhood radius, or a border point, which is not a core point, but falls within the neighborhood radius of 1, so it joins that cluster, or any point that is neither a core or border is labeled as noise. So DB scan is not like k-means because for it does not make any assumption about the cluster shape, and hence it can find clusters of any geometry. DB scan learns in such a way that it estimates the density distribution of the data, and there is no loss function or iterative optimization. So DB-scan is a fully deterministic algorithm that maps the density structure of the data directly. We are going to look at the parameters and hyperparameters of our DB scan. And first of all, we are going to look at the neighborhood radius. The neighborhood radius in DB scan is not set manually, but rather chosen from the k-distance graph. So we saw the distances to the kth nearest neighbor for every point in X scaled, and look for the elbow, which is where the density drops sharply. The elbow value then becomes our neighborhood radius. Moving on to our mean samples, which is literally set to twice the number of dimensions. So always around 14 for our 7 feature data, or a smaller value like 5 for noisier data sets. Our algorithm is set to auto as its value so that sklearn selects the most efficient tree structure based on the data size. Next, you're going to move on to our explainable AI techniques in DB-scan. Our DB-scan explainable AI techniques are built around making noise and parameter choices fully transparent. And for the first technique, we have the KNN distance plot. And this one makes this plot makes our neighborhood radius choice fully auditable because it displays the sorted distance curve with an automated new marker showing our chosen neighborhood radius value. Yeah. The grid research results table then prints the top 10 dB scan configurations showing the neighborhood radius, mean samples, number of clusters, the noise percentage, as well as the silhouette score, which justifies our chosen configuration, and this is present in our notebook. The noise point audit reports the fraction of riders labeled as noise as both a number and a chart bar, whereby a high noise rate would signal sensor artifacts or data distribution shift. The PCA scatter with gray noise plot overlay actually shows exactly where the biomechanical feature space where the anomalous riders sit, whereas the confusion matrix uniquely excludes the noise-labeled riders using the core mask before computing accuracy and reports that exclusion rate separately. This slide goes ahead to show us the explainable AI techniques we have just talked about, as well as the next slide before moving on to our next model. Our third model is the agglomerative clustering, which is also called the hierarchical clustering model. And this one is a bottom-up hierarchical method, which starts with every cyclist as their own individual cluster, and then repeatedly merges the two most similar clusters until only one cluster remains. We are then able to cut this hierarchy at the level that produces the three tiers we just talked about in the previous slides. Agglomerative clustering learns the hierarchical structure of the data by gridly merging the most similar clusters. The learning objective is basically to build a tree that minimizes the total within cluster variance at each merge. Thus, there is no iterative optimizations and the hierarchy is deterministic once the leakage and metric are fixed. Well, in agglomerative clustering, we are able to capture the merge history using a dendrogram. Yeah. More, the architecture of agglomerative clustering is as follows. The input is still X-scaled with 7 features per rider, and we use the word linkage with Euclidean distance, whereby the algorithm computes the pairwise distance matrix starting with n-value clusters, and at each step it merges the pair that minimizes the increase in total within cluster variance, which is Watt's criterion for the algorithm. The distances are then updated using the Lance-Williams formula, and the full merge history is passed down to the dendrogram function, and agglomerative clustering cuts the tree to output 3 final cluster labels. Well, according to our project, agglomerative works in such a way that every cyclist starts with their own cluster, and at each step, the algorithm finds the closest pair under Watt's linkage and merges them. The distance matrix is then updated via Lance-Williams method, and this continues until only one cluster remains, and the resulting dendron is cut at the height that gives 3 tiers. This process is a very deterministic process, and the same data always produces the same dendrogram. Well, the text accuracy according to agglomerative clustering is that it achieves a 100% accuracy across all the 3 tiers based off the 934 samples in the test split with precision, recall, and F1 score all at 1.0, and out of all our 4 models, this is the one with the strongest classification, whereby high skill covers 667 samples, the moderate covers 58, and the developing covers 209 samples. Next, we are going to move on to the agglomerative parameters stroke hyperparameters. For our parameters, we have the first parameter as the number of clusters, which gives a value of 3, which is chosen by inspecting the dendrogram for natural gap points and confirmed by Silhouette score. Our linkage criterion is WORD because it is the right choice for Euclidean distance, as it minimizes the within cluster variance at each merge, producing the most compact and well-separated tires. For the distance metric parameter, we are going to look at Euclidean because it is what is required by the word linkage to be able to be computed. For the compute full tree, our value is auto, meaning that the algorithm stops building the tree as soon as the required number of clusters is reached. Moving on to our agglomerative explainable AI techniques. Still, we have 5 techniques here, and the first one is the dendrogram, which is the primary interpretability tool, which shows the full merge history. For example, which riders are the most biomechanically similar, at what distance the tire boundary forms, and where to cut each tree. Moving on to our silhouette plot, it uses the silhouette score on the aggregate labels to check that clusters remain internally tight after cutting, which is very important because agglomerative clusters tend to be unequal in size. Moving on to the composite score box plot, which is unique to the model because it plots the distribution of each rider's composite skill grouped by tire, showing the tire purity and the presence of outliers, directly informing gate screening policy. And well, the between cluster variance is also important in enabling direct comparison of which biomechanical features drive separation under hierarchical versus centroid-based partitioning. And for our confusion matrix, it tests KN propagated tire labels on held out data, verifying whether the hierarchical boundaries transfer clean to new riders. Yeah, so the next slide is going to be showing us, this is a demonstration of the dendrogram that we've been talking about. This is the visualization of what it should look like. Then this slide also shows the explainable AI techniques we've just talked about, whereby we have the between cluster variance here, we have the silhouette plot here, we have the agglomerative explainable technique here, which is the composite score per cluster, which we've also talked about previously in the explainable AI techniques. Lastly, we have the Gaussian mixture model, which is the last model we are going to be training. And this one models the data as a mixture of k multivariate Gaussian distributions, where each component has its own mean, covariance, and mixing weight. And it is a soft clustering method where each point has a probability of belonging to each component. The parameters are estimated via the expectation maximization, which in short is the EM. Moving on to the GMM architecture, we have the input as X scaled, which represents also 7 features per rider, and the EM algorithm alternates between 2 steps, The first one being the E step, which computes the responsibility, which is basically the probability that each cyclist belongs to each Gaussian component. And the next step is the M step, which updates the component means, variances, and weights to maximize the expected log likelihood. This repeats until convergence, and the output is the hard labels from GMM predict stored in the DF chain GMM cluster column, and soft probabilities from GMM predict probability stored as GMM max probability, which is the highest probability assigned to any single tire for each rider. For our test accuracy, GMM achieves a 94% overall accuracy on the 934 test samples we've used, whereby for high skill we score 0.99 precision and 0.93 recall. For developing, we score 0.97 for precision, and for moderate, we score 0.85 for precision and 0.97 for recall. For moderate, we score 0.97 precision and 0.94 recall, as well as 0.96 for the F1 score. Yeah. Moving on to our GMM parameters, stroke parameters, we have the number of components K, which is given a value of 3, which is validated by the BIC curve, hence showing us that a lower BIC means a better balance between the model fit as well as the complexity. Moving on, we have the covariance type, whereby our value is full, meaning that each Gaussian component has its own independent covariance matrix. Maximum iterations are valued at 100, together with our tolerance, which is valued at 1 exponent negative 3, whereby both these are default. Yeah. Lastly, we have the number of initialization, which is valued at 10, meaning that it runs the expectation maximization from 10 different random starting points and keeps the run with the highest long likelihood, preventing convergence to a poor local solution. Next, you're going to look at the explainable AI techniques under the GMM. We have 5 GMM explainable AI techniques, and starting with the assignment confidence histogram, which plots the distribution of the GMM max probability with the threshold lines at 0.70 and 0.90, which is 70% and 90%, such that any rider below 70% is ambiguous and automatically flagged for human review rather than receiving an automated tire decision. The soft PCA scatter is unique to GMM, whereby the marker size proportional to the GMM probability maximum, so it bounds the riders such that small dots appear and high confidence riders appear large, giving visual map of model certainty across the entire feature space. Moving on. Oh, sorry. Moving on with the BIC as well as the AIC curves. These are plotted against K, making the number of tires choice statistically auditable. And the selected K corresponds to the BIC elbow, which penalizes overfitting. And we have the feature profile per GMM component, which represents the mean feature values per component as a bar chart. They show the land biomechanical signature of each tire. And lastly, we have the confusion matrix, which tests side labels against a KNN reference. This brings us to the close of our presentation, of my presentation, with the last slides having the visualizations of the explainable AI techniques I've just talked about. Thank you so much for listening.